Okay, very good then. So the topic I'd like to talk about today, well, okay, I should thank you for the invitation. I did it, but not everyone was there. So thank you very much for hosting my talk today at your online seminar. And the topic I want to develop in the talk is discussing limits of families of permutations and graphs which avoid substructures. And this talk is based on several papers with several authors. And what I would like to do in the talk is give an overview of what those works have in common and maybe also what differences are. Mostly I'm focusing on the common aspects. So the problem that I'll be considering during this talk is the following. I'll start with a family of either permutations or graphs, which is defined by the avoidance of substructures. So it can be pattern avoiding permutations or graphs which avoid some induced subgraphs. And in this family, I'll take an object of size n uniformly at random. And I denote by sigma n this random permutation in my class, or gn when I'm talking about graphs. And I'll be asking the following question: what does sigma n or gn looks like when n gets large? So I want to describe the global behavior of my permutation or my graph. A good framework to do that is by describing what the limits of the permutations in the permuton framework of the limit of the graphs in the graphon framework. So essentially, I'll define all that, but the point is to explain the picture that you see. This is the permutation matrix of a large separable permutation, so avoiding 2, 4, 1, 3, and 3, 1, 4, 2 as patterns. And if you repeat this experiment, you'll see similar pictures, although the crosses won't be in the same places. And we want to explain that picture that we see, and we can play the same game with picking uniformly at random a graph with no induced path on 4 vertices and plot the adjacency matrix, and we see something like that, and we would like to explain those global behavior of our objects. So both in the permuton and the graph case, permutation and graph case, I'll follow the same strategy for the proofs. So although these permuton and graphone allow to describe global limits of my permutations and my graph, they have a characterization through something that is not global at all. You can say it's local if you wish. And the point is that the graphon or permuton convergence is characterized by the convergence of the densities of all substructures. And that's how I'll access the permuton and graphon convergence in all cases. So to describe my permuton and graphon limits, I want to compute this density of substructures and see how it behaves when the size goes to infinity. And to compute these densities, I'll encode my permutations and my graphs by trees using the substitution decomposition of permutations or the modular decomposition of graphs. And doing so, you represent let's say a permutation by a tree where the internal vertices carry declarations which are themselves permutations, and the same thing in the graph setting. But nevertheless, this tree encoding has something very nice about it, that you can read induced substructures, also patterns or induced subgraphs, on the trees as trees induced by a set of leaves. So that allows you to access these densities of substructures by looking at how the trees induced by leaves in this encoding. So now a bit more computationally, let's say, with this encoding, how do I compute these densities of substructures? I'll express these as quotient of coefficient of generating functions. And I'll analyze the corresponding generating functions using analytic combinatorics to obtain asymptotic estimates of these coefficients, and then deduce my limiting densities of substructures. So that's the general strategy for the proof. I'll explain things in a lot more detail throughout the talk. So that's good if you get a feeling, but you don't have to understand everything I said, for sure. Something that is both nice, well, that I find nice about this strategy is that it's general. You can apply it to many families, but of course, like every general strategy, it won't always work. So although I phrased the title of my talk by saying I'm looking at limits or families of permutations and graph defined by avoidance of substructures, the essential property that I want about these families is that the tree encoding is nice. So the family of trees that encode the substitution or modular decompositions of my object has to be well behaved in some way. So this is certainly a very restricted framework, but nevertheless, that especially in the permutation case where we have quite many results, this covers most of the cases whose permuton limit is known in the literature. And so this strategy is very general, but I'll illustrate it on mainly one example during this talk, which is the family of co-graphs, the graphs avoiding an induced path on 4 vertices. And I'll discuss a bit the analog in the permutation setting, which is the family of separable permutations. So those corresponds to the 2 pictures I've shown in the first slide. And I'll also mention some generalizations to more families you'll see, to illustrate how widely you can apply these methods. So that's the end of my introduction. And I forgot to tell you that if you have questions, you can, of course, interrupt me. If you don't, I'll start moving to the first few definitions in this talk.
So just a quick question. Are you going to find the limiting graphon on Permutation, or just prove that one exists?
So in the talk, I'll prove that it exists because I compute all the densities of induced substructures, but I'll mention that we can also construct it and notice that the graphon we construct has the same density of substructure, so that's the one. But I won't in this talk do the construction. I couldn't fit everything. But I think I've once presented a talk which was recorded on that topic. So if you're interested, I can maybe email a link about those details.
Sure.
So let me move on to maybe basic definition about induced subgraphs and patterns in permutations and how this relates to permuton and graphon convergence. So if I would say that everyone says that a subgraph little g, a graph little g is an induced subgraph of a graph big G if you can pick vertices in big G whose which induce the edge such that if you keep all edges between vertices that you have picked, you recover exactly your graph little g. So the point of induced subgraph is that you are forced to keep all edges between the vertices that you have chosen. You're not allowed to erase any edge that you would like not to have. So that's how you define induced subgraph in a graph. And then you define the hereditary family of graph as set which is downward closed for the induced subgraph relation. So meaning that whenever you have a graph big G in your class, every induced subgraph little g that it contains is also in the class. Downward closed. So the family of co-graph that I want to discuss is a hereditary family of graph, but you have many, many more. I've listed a few, but this list is very small compared to what you can find. And that's somehow the way from the top to define a hereditary family of graph, but you can also see it from the bottom and characterize every hereditary family by avoidance of induced subgraphs in a set that can be either finite or infinite depending on your class, but that's the other view, which justifies a bit the title. So hereditary families of graphs are defined by the avoidance of induced subgraphs. So as I mentioned in the introduction, I'll be interested in the densities of induced subgraphs. So it's defined in this way. If I take a graph little g, and I'm trying to define the density of this graph little g as an induced subgraph in big G, well, it's essentially the probability that when I pick k vertices at random in big G, k being the number of vertices of little g, the subgraph that is induced by these k vertices that I've chosen is equal to little g. So I have to be a bit careful about how I pick these vertices at random. That the definition that works best somehow is to pick k times vertices uniformly at random and independently, which allows you to have twice the same vertex. So that's a bit undesirable, but that's still the definition that works best for the next slide. I just want to point out that you can define a variant of this density, which is sometimes called the injected densities, where you pick your k vertices as a k tuple of distinct vertices and uniformly at random among those k tuples. So then you avoid picking twice the same vertex, of course. And although these quantities are different in general, if you look at a graph G of size tending to infinity, they will coincide. So the property that is correct and that I will need is that you will have convergence of the densities of little g in a graph Gn as n tends to infinity in expectation to some quantity, if and only if the same quantity with the injective density converges to this same limit delta g. So you can essentially choose one or the other. It won't make a difference for my purpose. So that's for the density of a graph little g in a graph big G, but I will be interested in densities of graphs in graphones, which generalize graph in some way. So let's review or explain, I don't know, the background that you have, what graphones are. So that's informal, but that's enough for my purpose. First thing I want to do is to let you know how you build a graphone from a finite graph. So I've chosen a finite graph here on the left, and I can encode it by its adjacency matrix for any order on the vertices. Here it's from left to right, I believe. And this adjacency matrix I can represent by a function on the unit square, which I build by just gridding the unit square so that I have a little square for each entry of my adjacency matrix. And whenever I had a 0 in my adjacency matrix, I put the image 0 in the corresponding little square and the image 1 when I have a 1 in the adjacency matrix. So I obtain a function of the unit square to the unit interval 0, 1, which actually takes only values equal to 0 and 1, but that encodes my original graph through its adjacency matrix. And this is almost a graphone associated to my graph G, except that I want to consider this function up to the action of permuting the rows and columns of my adjacency matrix, essentially applying the same permutation on the rows and the columns. So now those were the graphone associated to finite graphs, but the interest of this notion is that it generalizes to the continuous, so that you can encode somehow infinite graphs with quotation marks around that. And a way to define a graphone is very similar, at least intuitively, except that you replace the adjacency matrix that you start from with an possibly infinite matrix that may have a continuum of rows and columns, and which remains symmetric and takes value in the interval 0, 1. So if you imagine you have such a symmetric matrix with a continuum of rows and columns and value is the interval 0, 1, you can still build the associated function of the unit square and consider the equivalence class of this function for the action of permuting rows and columns, again with the same permutations, and that defines a graphone. So I've talked earlier about the densities of induced subgraphs in graphs, but I want now to generalize that to graphones. And if you remember, the density of little g in big G was the probability that when I pick k vertices at random in my graph G, k being the size of little g, the subgraph induced by those k vertices is equal to little g. So I want to copy this definition in the graphone and define the densities of a graph little g with k vertices in a graphone W as the probability that when I pick k vertices uniformly at random, etc., in my graphone W, these k vertices induce the graph little g. So what does it mean that you pick vertices at random in a graphone and that they induce something? That's what I need to define. Well, if I go back to my picture earlier, the vertices, they were corresponding to rows and columns in my matrix here in the finite case. So if I move that to the continuous, what I want to pick uniformly at random is indices of rows and columns in my infinite matrix. So it means picking reals in the intervals 0, 1, the reals x1 up to xk, and those correspond to the indices of the rows and columns I want to choose. And then I will look at somehow induced matrix so I choose a representative of my graphone W, let's call that little w. And I look at the matrix that xi induce for this function, function W. So for each pair xi, xj, I read a value which is a real between 0 and 1 with the function W. And that gives me the probability to connect the vertices corresponding to xi and xj, which I call vi and vj. And that's how you define the graph induced by k vertices that you pick uniformly at random in your graphone W. Is the definition decently clear? So the point that I want to make is also that this properly generalized the definition of the density of subgraphs in graphs, meaning that if you look at the graphone associated to a graph, you have this equality, and to have that, I needed to consider the non-injective version of the density. That's essentially why I had the two definitions earlier. Okay, so I'm moving a bit into the graphone theory, but just keeping things very basic somehow. What I will want to do is to be able to speak of convergence to some graphone. I'll have my random choreographs, for instance, and I want to ask the question, what is the graphone limit? So to do that, I need to be able to speak about convergence in the world of graphones. And that's possible, although it's not so easy to do, because to make the space of graphone matrix is not an easy task. You need to define a special distance on that set, which is the cut distance, and then you need to quotient with an equivalent relation to make the space matrix. But anyway, it's possible. And because you end up with a compact space, you are somehow justified to have made this complicated construction. And that the whole point for me is that it allows you to make sense of the notion of convergence for graphones. And so of course, if I can speak about the convergence of a sequence of graphones to some graphone, but what I will want to do, and what many people do, is that you take a sequence of random graphs, or maybe not random, a sequence of graphs, Gn, you look at the associated graphones and you want to look at the limit there. Typically, the Wn that you find are not infinite graphones, they are just graphone coming from discrete graphs. And that's what I will do in this talk. And you can, in this context, you can maybe rephrase this notation for convergence, but just this notation here, that the sequence Gn of graphs converges to the graphon W. So I have not defined what convergence of graphon is. I've just told you that it's possible to do it. The point is, it has a very combinatorial characterization, which is all I need in this talk, and which is the following. You will have convergence of a sequence of graphon Wn to a graphon W if and only if for every graph little g, so a finite graph little g, you have convergence of the density of little g in Wn to the density of little g in W. So proving the convergence of all those densities completely characterizes graphon convergence. So far, and that's written here, I've stated this criterion of convergence for deterministic, for a sequence of graphs Gn, which is deterministic. Gn is a deterministic graph, and consequently, the limit is a deterministic graphon. But what I will want to do is to take Gn random, like a uniform random cograph with n vertices. So you could imagine, and it's true, that this criterion for convergence extends for convergence in distribution, that you will have convergence in distribution of your random Gn to W, if and only if you have convergence in distribution of the densities of all induced substructures. That's true, but even more is true. You only need convergence in expectation of the densities. Indeed, so these it comes from those two results. Maybe the first one is only used in the second one, let's say. So I'll discuss only the second one. If you want to prove that some sequence of random graphs Gn converges in distribution to some graphon, random graphon W, it's enough to compute the limit of the expected densities of all induced substructures in your graphon. And it's very much easier because those things are numbers, while the densities of induced substructures were random variables. These objects are really much simpler than discussing the distributions of those random variables a priori. So that's the criterion that I will use throughout the talk to prove graphon convergence or similarly permuton convergence, as I will discuss. All right, so summarizing what I've said so far, I've defined induced subgraph, with difficulty, but made it, and then hereditary classes of graphs. I've presented in parallel the notion of what a graphon is, which essentially means that you take an adjacency matrix, you rescale it to the unit square, and that describes your graph, and you push that to the continuum. And those two notions relate because to prove graphon convergence, it's enough to prove convergence of the densities of induced substructures, induced subgraphs. And you can do it only in expectation if you have a sequence of random graphs whose convergence you want to prove. So what I want to do next is define parallel notions in the realm of permutations instead. So analogues of those 4 items for permutations. So throughout this talk, when I speak about permutation, I can maybe represent it by the sequence of its images from 1 to n. So I view it as a word, but mostly I view it as its permutation matrix, which I call sometimes the diagram. And my convention for permutation matrix is that the cell 1, 1 is here. So it allows me to represent this permutation by the set of points at coordinates I, sigma of I. So this is the permutation 3, 1, 2, what is that? 7, maybe 8, etc. And you defined an induced substructure, if you want, in a permutation as what is called a pattern, as follows. To exhibit a pattern in this permutation, I need to pick some points and just keep the rows and columns that are not empty in what is left of my permutation matrix. So that amounts to that. And so here the pattern 2, 1, 4, 3 is a pattern of my larger permutation, and this displays an occurrence of the pattern in the permutation. Okay. So that's what the example says. I'll win a bit of space to tell you that from patterns you define permutation classes, just like we defined the hereditary families of graphs earlier as sets that are downward close for the pattern relation. So that's the way from the top, but if you read from the bottom, permutation classes can also be characterized by the avoidance of patterns. Okay, so that's for the type of object that we look at. Now let's move to the framework where we want to establish our limit results, and that's the framework of permutons, which is much simpler than the Graphone framework. Also, it shares some analogy with it. Now, okay, maybe I'll do the example first. If I have some finite permutation, I can represent it through its matrix by a function of the unit square. So that's again my unit square, which takes values equal to 0 or 1. Not at all, which is a probability measure on that unit square. So how do I define this probability measure? I just look at the cells that were containing a dot here. I look at the corresponding cells, small squares in my unit square, and I put some mass on those little squares, and I distribute the mass uniformly on those gray squares. So that's how, from a permutation and its matrix, I can build a probability distribution on my unit square. And this probability measure on the unit square has the property that if you cut a vertical strip or a horizontal strip, then the total mass that is on this strip is equal to the width of the strip. So that's the property that appears in gray here. And a permuton is exactly the infinite generalization for the number of, I don't know, the size of the grid that you put here, because you define a permuton as a probability measure on the unit square whose projections or marginals are uniform. So the probability measures you consider must have this property that when you cut a horizontal or vertical strip, the mass on that strip is equal to the width of the strip. So that defines the permutons. Okay, and the idea is similarly that, okay, the permutons can represent finite permutations, but they can also represent permutations of infinite size. So that's the analogues of the graphone from the previous part of the talk. Okay, now because permutons are probability measures on the unit square with uniform marginals, but nevertheless they are probability measures. So it makes sense immediately to speak about convergence for permutons, because we have the weak topology for measures that provide us with a notion of convergence there. So it's not difficult, unlike the graphone case. And so I'm now allowed to speak about what it means for a sequence of permutations to converge to a permuton mu in the deterministic or in the random case. And we have, similarly to the graphone setting, a characterization of the permuton convergence by convergence of the density of substructures. I tend to say frequencies of patterns there, but it's exactly the same thing. And I haven't given a formula for this, but I'm counting the number of occurrences of a pattern pi in sigma, and I'm normalizing by the total number of occurrences that may exist, which depends only on the size of my pattern and my permutation. And you can define the frequency of occurrence of a pattern in a permutation, in a permuton mu, just by saying, okay, I pick points in my unit square depending on the measure that I have on my unit square, and I look at the diagram that this point forms to describe the permutation. So you have really this convergence of frequencies of pattern which characterize permuton convergence in the deterministic case, and it extends to the random case as earlier. And again, we only need the convergence in expectation. So if we can prove convergence in expectation of the frequencies of occurrence of every pattern in a random permutation, sigma n, then we characterize the permuton limit of my random sequence sigma n. Okay. So that's really the analogy. I've been a bit quicker on the permutation case, but everything maps very nicely from the definitions that we had on graphs on permutations. All right, so as I told you at the very beginning, for my purpose of computing permutons and graphon limits of some families of permutations and graphs, I want to encode my permutations and my graph as trees. And that's the second topic that I want to discuss in the talk, that you have all the tools that I need in the proofs. So, okay, I forgot to, I'm not good at putting bibliography in the slides, but everything I've said so far is essentially folklore in the graphone / permutons literature, except maybe, sorry, I'm coming back, the generalization to the random setting here, but I think that's something we made clear in a paper, but it's very classical. And again, this technique of decomposition trees is also something very classical that you can find in the literature in many places. That's not something new at all. Okay, so but just for completeness, let me go very basic. So the trees that encode my graphs are what is called modular decomposition trees. So I need to tell you what the modular decomposition is, and of course this relies on the definition of what a module is. So if you have a graph G, let's say that graph here, a module in this graph is a set of vertices which cannot be distinguished from the outside. Meaning that whenever you have a vertex outside of your module, it's adjacent either to everyone inside the module or to no one inside the module. And if you pick, for instance, the set of green vertices in my picture here, this set of green vertices is a module. And if you pick, because if you pick anyone outside, either it's adjacent to everyone in green, that's the case for the red, or to no one in green, and that's the case for all 4 other vertices. And you can check that every set of colored points here is a module of my example graph. So now assume I have a graph G and a partition of its vertex set into modules, like the colored partition that I'm showing here. Then I can somehow encode this graph equipped with the partition into modules by the structure that I have on the left, which is the beginning of a tree. It's a quotient graph, which I obtain by keeping only one vertex in each of the modules, and by looking at the induced subgraph by this set of vertices. So if I keep one green, one red, one purple, and one blue vertex, the induced graph that I have is a path of size 4. That's the graph that I here is my quotient graph for this partition. And below, I'm saying that I'm inflating each vertex by a smaller graph, which is a factor, and which is the graph induced inside one of the modules. So the graph in green is the graph induced by my 3 green vertices, etc., etc. So the graph in blue is that one, the graph in purple is this one, and in red there isn't much to say. Sorry. So as I was saying, this is the beginning of a tree, because now in the graphs that I see here in the factors, I can repeat this process to continue and build a tree. And that would be one modular decomposition tree of my graph G. So this graph is, this tree is a rooted tree. That's quite visible from the picture. It's a non-planar, but I have a correspondence between the child of every vertex and the vertices of the graph that label it. And in the end, the leaves of that tree will correspond to the vertices of my graph. If I keep going. Oh, so here I have continued and I have this correspondence between the vertices of my graph and the leaves of my tree. The point is, so far I started from any partition of the vertex set of my graph into modules. And if I do that, I don't have a bijective encoding. So that's not very good for my purpose of having an encoding. You know? But you can force this modular, so, I mean, you can find a unique modular decomposition tree which represents your graph and is canonical when you consider the coarser partition into modules at every step, essentially. So the theorem that you obtain, and I'm not explaining the details there, but there is a unique tree corresponding to every graph whose vertices are labeled by either prime graphs, and this means that they contain no non-trivial module, trivial being empty, the whole set of vertices, or just isolated vertices. So those are always module in the graph. So if they are the only ones that you have, you say that your graph is prime. So now I'm coming back to my theorem. Sorry for the messy presentation. So to every graph, you associate uniquely a canonical modular decomposition tree, whose which you build as I described, and whose vertices are either prime graphs or cliques. So I have small cliques there, or independent sets, and I have small independent sets there. And such that you have no edges between two independent sets, nor between two cliques. Those conditions are necessary if you want to have a unique representative, which is something I want to have. So because I'm not presenting the details of the construction, is very mysterious there, but you have this unique encoding of your graphs as trees, which satisfy these conditions. Now, what is very interesting for me is that I can read induced subgraphs on these decomposition trees. And remember that induced subgraphs are the thing that will characterize my graphone convergence. So I'm very interested in those. Okay, so I've chosen an example of a graph here on the right, and in blue, I've picked a set of vertices, and I want to look at the induced subgraph, the subgraph induced by the blue vertices. Here on the left is the canonical tree which correspond to this graph here. So it doesn't have any prime graph, just cliques and independent sets, the 0 and the 1s, and they indeed have no 0, 0 edge, no 1, 1 edge, so that's good. So remember the vertices in my graph correspond to leaves in the tree. And if I follow the decomposition, these blue vertices correspond to the blue leaves here. And if I look at the subtree that these blue leaves induce, they describe the blue subgraph induced by the blue vertices there. But although I started from a canonical modular decomposition tree of my graph, my big graph, the subtree that I obtain, the induced blue subtree, is not necessarily canonical. Here you see that you would have an edge between two vertices, two internal vertices labeled 0, because I don't need this one in the middle. I'm not branching there, so I'm just moving through. But nevertheless, the blue tree that is induced there encodes my induced subgraph there. Essentially because those internal vertices tell me where there are edges between the blue vertices. It all works. It's a bit mysterious again, but that's somehow just a tool that I need. I ask you to trust me with that. Okay, so very quickly, I just mentioning the analog notions for permutations, which share really the same property. Instead of a module in a permutation, we talk about intervals. So there are really boxes like the red one here. They correspond to a set of points whose value form an interval as well as, whose position form an interval as well as their values, meaning that they cannot be separated by other points. Separated meaning someone that would, I don't know, sit in the middle, either horizontally or vertically. So the shaded area are empty. So that generalizes, but parallels nicely the notion of module in a graph. And now, if I have a permutation seen as its diagram and a partition of the points into intervals, I can again represent that by a quotient permutation inflated by factors permutations. The quotient is just the permutation I see by comparing how my intervals are placed. So that's a 1, 3, 2. And inside, which corresponds to my quotient permutation, and inside I have smaller permutations, so 2, 1, 1, 3, 2, etc., which I inflate in those elements of my 1, 3, 2. So that's how you start your tree somehow. So if I want to have a canonical tree that encodes my permutation, I needed to be careful to use quotient permutation that satisfy some analog properties than the prime graphs I had earlier. And a prime graph had no non-trivial module. Here in permutation, we speak about simple permutations, but it's exactly the same thing. They are the ones with no non-trivial intervals, so only trivial intervals. And then you can represent uniquely every permutation by a tree, which is the substitution decomposition tree. And it's the tree whose internal vertices are labeled either by simple permutations or increasing permutations, which are called plus, decreasing permutation, which are called minus, and such that you don't have edges between plus nodes nor between minus nodes. So this encoding again is unique, provided you require these conditions. And you have exactly the same property that if you look at a pattern induced by a set of points, like the blue points here, you can read the pattern by looking at the tree induced by a set of leaves, which correspond to your blue points. And even if you start from the canonical tree, which represents your permutation, the blue tree that will be induced is not canonical a priori, but it still describes your pattern. All right, so, that's the summary of this part about trees. So the whole point is that using this substitution decomposition of permutation or modular decomposition of graph, you are able to represent a permutation or a graph by a tree which is decorated. It carries graphs and permutations on internal vertices. In that you have nice way of reading induced substructures as subtrees induced by set of leaves. So one difference between the trees associated to permutations and to graphs is that for permutation you have planar trees, and with graph non-planar trees, which makes things a bit more complicated when you put that into the symbolic combinatoric frameworks, as we will do, but okay, it's still doable. Maybe I skip the remaining part of the talk. I'm not sure this makes a lot of sense for me to discuss at that point. Sorry. Okay, so finally, we get to discussing graphon limits of one of the simplest family of graphs that I can talk about in this context, which is the family of cographs. So we want to explain the pictures here that I've shown at the very beginning. So maybe you remember I very quickly defined cographs at the beginning of the talk. They are the graph that avoid an induced path on 4 vertices. But most importantly for us, the cographs are those whose modular decomposition tree contain no prime nodes, only the cliques and the independent sets, so only 0, 1 nodes in the modular decomposition trees. And because they are the cographs, I sometimes call co-trees the associated modular decomposition trees. So if I want to describe cographs through their canonical co-trees, here is what I can do. I can consider this family L of trees, which is it's a recursive description. A tree of L is either a leaf or has an internal vertex with at least 2 children, which are themselves trees of L. And provided I have such a tree, if I decide for a label 0 or 1 to put on the root, and then I propagate labels to all internal vertices by forcing alternation between 0 and 1 along each edge, what I obtain is the set of canonical co-trees. So that really completely describes and bijectively describes the set of cographs that I want to study through their canonical co-trees. And we'll see that this family L, I mean, studying it from the analytic combinatorics perspective is a key step that we will need to do later. Okay, let me come back to what we need if we want to prove graphon convergence of uniform random cographs in the labeled case. That's a bit simpler. So I'll denote by G sub n now this uniform random labeled cograph with n vertices. And to characterize the graphon limit of G sub n, it's enough to compute the expected density or injected density, if I prefer, of every induced subgraph G in this G sub. So how can I express this quantity using the trees that now encode my cographs? So that's written here at the very bottom, and I'll guide you through the notation along the way. So the expected density of little g in my Gn is, by definition, the probability that when I pick k vertices uniformly at random when I pick a set of k distinct vertices uniformly at random in Gn, this k vertices induce little g. And now if I read this probability on the trees, this is the probability that when I pick k leaves in a canonical co-tree of size n, so that's what I'm doing here, then I obtain a tree T0 which encodes the graph little g. It doesn't have to be the canonical co-tree of little g, but some tree that encodes little g. So if I sum over all co-trees T0 which encodes little g, I can express this expected density of little g in my graph Gn like this. So now, how do I compute what is inside the sum here? So I'll express this quantity as a quotient of coefficient of generating functions. So remember the meaning of this probability here is the probability that when I pick k leaves at random in a uniform labeled in a uniform co-tree of a canonical coterie of size n, then they induce T0. So I really express this probability as the number of good cases divided by the number of total cases. I have a good case when the k-leaves that I've chosen do induce T0. And on the bottom, it's just the number of ways I can pick my k-leaves in my tree. So that leads me to define the following families whose generating functions appear here. T0 being fixed and with k-leaves, M sub T0 is just the set of canonical coteries that have k marked leaf inducing T0. So when I extract the coefficient of Zn in the exponential generating series, and then I multiply by the factorial because it's an exponential generating series, I just find the number of canonical coteries with k marked leaf inducing T0. So that's my number of good cases. And to find the number of total cases, I'll just count how many canonical coteries with n leaves exist. So that's taking the coefficient of Zn in the exponential generating series of canonical coteries with the factorial m for the exponential part. And then I'm picking k-leaves. So I'm picking the first leaf, the second leaf, etc., etc. And I have this factor that appears at the bottom. So because I've been able to express this probability as a quotient of coefficient of generating series, you guess that what I want to do is use analytic combinatorics to estimate those coefficients of generating series. So I'm somehow assuming that you're familiar with the general idea of analytic combinatorics. If you're not, that's a bit magic. And I apologize for this, but I cannot cover all background in a talk. So, all right, my point here is to estimate my denominator, so the coefficient of the series M. And the series M is expressed very simply in terms of the generating function for the family L that I had at the very beginning. You remember my trees L that were consisting of either a leaf or a root with at least two trees below it, which are themselves in L. This symbolic way of describing the family L translates immediately with this symbolic combinatoric framework into an equation for the exponential generating function for L, which is the following. L is equal to Z plus exponential minus the first two terms of the exponential of L of Z. And so you can well, analyze the behavior of the generating function L based on this equation for L, and obtain that the radius of convergence is this value rho, and that the behavior near a row of your series L is the following one. So that's the typical tree behavior with a square root that you find for all families of trees, essentially. And then you immediately deduce from this the behavior of M near this same radius of convergence. So that this formula here is just explaining the fact that to build a canonical cotree, what you do is you choose a tree of L and choose a sign on the root. That's 0 or 1. That's why you have the 2, and then propagate the sign. But if your tree had just a leaf, you don't have a sign on the root, so you have this correction factor effect. That's no big deal. Anyway, once you have the behavior of your series M near its radius of convergence, you deduce using the transfer theorem of analytic combinatoric the behavior of the coefficients of your series M. And it's the typical tree behavior with a row to the minus n to the minus 3/2 times a constant. And I've included here the n to the k factor that amounts to choosing k leaves in my canonical cotree. So that now I have asymptotic estimate of my denominator in this expression for the probability that I'm interested in. The numerator, it's a bit more complicated, but you can still relate the series MT0 to the series L with some weird variance. And you somehow do that. I like this picture that describes the proof. The idea is really just that you look at your tree T0 and how it, when you have k-leaves that do induce T0 in a big tree, how it breaks down the big tree into pieces which correspond to the edges of your tree, little tree T0, and you look at the generating function of all those pieces, you combine them together, and that's how you describe, do you obtain this, this complicated expression for M0. It doesn't explain the mystery totally, but a little bit maybe, I hope. Anyway, even though this expression is complicated, from the behavior of L at the radius of convergence, you deduce the behavior of MT0 at the radius of convergence, and hence, using the transfer theorem, an asymptotic estimate of the coefficients as n tends to infinity. The interesting case of this estimate is when the tree T0 is binary, because in this case, all the exponents that I have here simplify nicely, and I obtained an asymptotic estimate for the coefficient, the numerator in my probability, which is exactly what I had earlier for the denominator times this combinatorial factor in front. So now I just do the quotient of numerator and denominator, and I retrieve this combinatorial factor that is the limit of the probability that the cotree induced by k-leaves that you pick in a uniform random canonical cotree of size n is equal to T0 when T0 is binary. But this is just the inverse of the number of binary cotrees. That's a very easy observation to make. So if T0 were not binary, the probability needs to be 0 because you don't have space for those. And it's also very natural. If you think of a big canonical cotree, you pick k-leaves in that and you look at what they induce, you will never have a branching node with 3 children. You will only find binary branching nodes. So but you find it with computations there also. So now that I have obtained these quantities, I just need to sum them up over T0, binary, the other ones don't count, to obtain the expected densities of induced subgraph little g in my random cograph Gn, summing over all T0 encoding little g. And as we have discussed, those quantities, they characterize completely the graphon limit of cographs. So here I've proved that the limit exists and that it's characterized by these quantities, but I haven't constructed it, as was asked at the beginning of the talk. It's possible to construct the limit really by mimicking in the continuous the induced sub-reconstruction that we do on the trees of size n tending to infinity. So instead of tree, we have the limit of the trees is somehow the Brownian excursion, even though you have a rephrasing somewhere. But my point is, you can build this limiting graphon of random cographs, which we have called the Brownian cographon, by starting from a Brownian excursion, putting decoration 0 and 1 on the local minima corresponding to the internal nodes in your tree somehow, and pushing that to a continuous version of the bijections between trees and graphs that we had earlier somehow. Then to prove that this is indeed the correct limit, we just compute the densities of subgraphs and observe that they are the same quantities than what we had, oops, sorry, on the previous slide there. Those are the delta G that we find here. Okay, so I'm not doing that in this talk, but that I just wanted to mention it because this is not just a proof of existence, we also have a construction. And because the construction relies on this Brownian object at the beginning, it explains the somehow fractal picture, fractal aspect of the picture that we had here, because the Brownian excursion is itself fractal in some sense. All right, so I have just one slide to discuss the Permuton analog of this result about cographs, which speak about separable permutations, and then I won't be formal and will just present briefly extensions. Okay, so the separable permutations can be described as those avoiding the patterns 2143 and 3142, but there's another way. They are equivalent characterization, and the way I want to see them is as the permutation whose decomposition tree have only plus and minus nodes. So here you really see that it's the analogues of the cographs, where I had just trees with 0 and 1 decorations. And we can apply the same proof strategy. We describe the decomposition trees of the separable permutations by a combinatorial specification. We use analytic combinatoric on this specification to compute the limiting behavior of the number of occurrences, sorry, the frequency of occurrences of patterns in uniform random separable permutations in expectation, expressing this as a quotient of coefficient of generating functions that we access with these analytic combinatorics tools. And that characterizes completely the permuton limit of separable permutations. And if we want, we can build this permuton limit explicitly, starting again from our Brownian excursion. And we just compute the densities of induced patterns there to observe that it's the correct limit. So we really do a similar proof, and that's actually what we first did. We did the permutation case before the graph case. Maybe the only point I want to make is that I have this notation mu a half for the permuton limit of separable permutation, and I call this the Brownian separable permuton of parameter 1/2, and we will see that I want this parameter to vary later on in my generalizations. Okay, so let's relax and talk about the generalizations very without entering details at all. If I try to summarize the method that I've used, it's essentially the following. What I need at the beginning is a description of the trees that encodes permutations in the class that I'm studying, a combinatorial specification more precisely that describes those trees. This combinatorial specification translates using symbolic combinatorics to a system of equation for the generating function of C. And in addition, because the patterns, they correspond to subtrees induced by leaves, I can track patterns in this system of equations that I obtain from my specifications. So if I don't have a problem in applying the method of analytic combinatorics, because I don't know, I would have 0 radius of convergence if something wouldn't work. If I don't have any such problem, I can apply the same method to obtain convergence to a certain permuton, just like we did for the separable permutations and the cographs earlier. And that's a schema that we have realized in 2 general contexts. The first one is the context of substitution closed permutation classes. And the second one is classes for which we have a specification. So maybe that's actually a second generalization. So in the substitution closed class, we always find Brownian separable permutons as limits, although the parameter varies. And whenever a specification is known, we find sometimes Brownian permutons and other times other permutons, which we called X permutons, and which are this time deterministic, based on a dichotomy that we read on the combinatorial specification already. And I'll discuss that a little bit. But first, the substitution clause classes. If you remember, the separable permutations were encoding by the trees with plus and minus nodes. So that corresponds to the left part of this specification here. So left of this vertical line that I'm trying to draw. What I'm doing now, if I consider a substitution closed class, is I'm allowing some prime nodes. That's what I'm allowing here on the right. But now, using this plus and minus and those prime nodes, I'm building all the trees that I want. So the family that I obtain is closed undertaking substitution. So if you have such a family with this combinatorial specification, you will always end up with a limit that is a Brownian separable permuton. So the unbiased case is the one on the right with the parameter 1/2 that we have for separable permutations. But you can have bias that force the permutation to be mostly decreasing or mostly increasing when P is close to 1. So again, we have our separable permutations, that's the basic case there. That's another example. Here I'm allowing 3 simple permutations in my trees, and I obtain the exact same limit, an unbiased Brownian separable permuton. And I have a third example. So this time I'm taking infinitely many simple permutations that I'm allowing. And we obtain a Brownian permuton whose parameter we don't know exactly, but is in this range, something close to 1 to 0.6. All right. So I'm now moving to the further generalization, where we have combinatorial specifications that can be more general than the one for the substitution clause classes. And in this case, we will, among all the families that occur in the specification, look at what we call the critical families. Those are just the one that dominates the asymptotic enumeration. So the one with smallest radius of convergence among all the families that appear in the specification. And then whenever your specification contains a product of critical family, you can ensure that your limit will be a Brownian separable permuton of parameter P between 0 and 1, possibly degenerate. A very simple example is the following: the permutations avoiding 1, 3, 2. I'm displaying a combinatorial specification for this family using the substitution decomposition tree. That's definitely not the most natural way to describe this permutation, but it's doable. And in blue, I'm representing the critical families, so the one that dominate the enumeration. And you see that some families occur as a product. Some blue families occur as a product, like here or here. So I have a product of critical family. I'm in this Brownian case of our dichotomy, and I will end up with a limit which is a Brownian separable permuton, although of parameter 0 here, so not a very interesting one. But for further examples, like this family of permutation, you have a specification which looks like the following, again with products of critical families in blue. So you end up with a Brownian separable permuton of parameter some real number a bit less than 1/2 that we can fully characterize. That's just what happens to be. Okay, so that's for the Brownian part of the dichotomy. The other part of the dichotomy is when you have no product among the critical families. We can show then that the limit is not random. It's a deterministic shape that you observe, and it's the shape of an X. So this class of permutation is known as the X class for a reason that you will see shortly after. We can obtain a specification describing the trees encoding permutation in the X class, and that's the following. Again, the blue families are the critical ones, and you never have a product of two blue families. This shows, I mean, that's the framework in which we have this deterministic X permuton as a limit. And in this case, it's a very centered X, so that gives the name to the X class. So that's a simulation of a large permutation in this class, that the theoretical limit, and you see that they coincide very nicely. That's another example with a bigger specification, critical families in blue, no product of critical families. And here again, you have an X-shaped limit, but that's not the same X. The center has moved a bit further down to the right. But you see that it describes very well the behavior of the simulations that we observe. And I have a final example there, which I wanted to display because sometimes you see a V, but that's just a degenerate case of an X with the lower branches being reduced to have height 0. So you explain all those observations by the same phenomenon of the X case of our dichotomy, let's say. So I'm almost done. I have 3 small remarks that I want to make as a conclusion. The case that I discussed the most in the talk is the case of the co-graphs with their graphon limit. And then I provided generalizations in the realm of permutations. The reason is that I don't have, for the moment, generalizations in the graph setting, but that's a very natural thing to do because the analytic approach could work very in the same way, provided that we have generating function with positive radius of convergence, which is automatic for permutations, but not for graphs. But if this works, the approach can be applied, and we decided with my co-author not to do that ourselves, but to offer that as a PhD topic. And a student started working on this project, supervised by my colleagues Frédéric Bassineau and Lucas Jorin in Paris. And so the name of the student is Théo Lenoir, and what he has been able to do is that this Brownian co-graphon, which is the limit of co-graphs, is also the limit of P for reducible graphs, P for sparse graph, etc., etc. You have a description of the families that he was able to study there. So I hope he can tell you more about that if you're interested in a couple of weeks now. The second remark is about my proof strategy of computing the densities of substructures using analytic combinatorics. For me and my co-authors, that was really the natural way to access those quantities. But for a person who is more a random tree person, there would be the option of computing these densities of induced subtree directly on the random trees that encode the random graphs or random permutation using classical techniques from the random tree literatures with some adaptations, because our problems are not exactly what is typically studied there. And that's doable. And we have done it with Jacopo Borga, Valentin Ferré, and Bénédicte Stufla in the case of substitution clause permutation classes, and Bénédicte Stufla did it on his own for the co-graphs. So that's an alternative part of the proof, let's say. You can replace the analytic combinatorics by a random trees argument if you prefer. And my final remark is about a nice consequence of these permutons and graphon limits that we have computed. So for me, I'm a person who studies pattern avoiding permutations typically. And being able to answer the question, what does a permutation in the class that I'm looking at looks like, describing the typical shape of a permutation that I pick at random in the class I'm studying, is a very natural thing I want to do. But if you're not interested in such questions, you can still find the Permuton and Graphone limit interesting for the following reason. Using this Brownian and the fact that cographs have the Brownian cographon as the graphon limit, we were able to deduce that they do not contain, that the largest independent set they contain is of sublinear size. And pushing things just a little bit further, this shows that the cographs don't have the asymptotic linear Hurdish-Hasnal property. And this is a question that was answered in the, that was asked by the random graph community, which we have been able to answer with our tools coming from a different field somehow. So that's an input that I've been able to provide to this community with our tools. And really the proof works from this Brownian limit that we have. We just compute the independence number of our limiting object and have some continuity, observe that it's 0 and have some continuity to deduce this result here on the top. And so naturally it has an analog in the permutation realm, showing that separable permutations can have longest increasing subsequences of sublinear size, typically, although this question was never asked there, but we can still answer it. And a bonus somehow of all this is that because it relies only on the limit, as soon as we have a class with the same limit, we deduce the same consequence, that you have no independent set of the largest independent set has a sublinear size. So that's a nice generalization. Okay, so that's where I start. I've been long. I hope you don't mind, and if you have questions, I'm happy to hear them.
All right, thank you very much for the talk. Are there any questions?
Yes, I have a quick question. So you're sampling your starting point, let's say for graphs, it's a uniform random graph. So it's,
yeah.
But you could also sample from GNP or from some graphon.
So I'm not at all. Yeah, GNP is a very orthogonal way of approaching random graphs. I think what I'm doing is that I'm looking at a class and I'm sampling uniformly at random in this class. So it's
yeah, but you can sample according to
a much
conditions
weaker
on
model in terms of random graphs, but it makes sense if you're interested in the study of this family of graphs.
I'm saying you can sample, so you're sampling GN half conditioned on something. So you can just sample GNP conditioned on something.
Okay. Then I don't know whether you would obtain the same limit. What I do know is I know 3 distributions on the cographs, which all will lead to this Brownian cographon. It's the uniform among the labeled, uniform among the unlabeled, and I pick a uniform separable permutation at random, and I build the graph associated with it as the inversion graph. And those are 3 different ones giving the same limit, but I don't know about one, I don't know, the GNP conditioned, whether it would.
So GNP seems so plausible that you can take
your. We want to do that anyway.
It seems plausible that your counting will work. You just need to add some weights somewhere.
That's a very interesting question. We never thought about it, and I'll give some thoughts to it, but I'm not able to think properly after the talk. I'm sorry.
All right. Are there any other questions? That doesn't seem to be the case. So thank you again, Mathilde, for the talk.